We'll wait for 2 minutes, right? For more people to join.
Or we can start with the intro right away, and then in the meanwhile, people are joining.
Okay, let me share the screen.
Yeah, maybe we can wait 2 more minutes and then start. Since a few other people are joining.
Yeah.
Meanwhile, I'd like to update everyone who's here that we have recently released some new updates, new nodes on Beegraphy, and I'd like to share the blog so that you can go through it and see what is new in the Beegraphy. Yes, then
I accidentally clicked on that button, but regarding the blog post, since you mentioned it, there are a few things that are, the plugin manager that we mentioned in the update. It's our first version. Will definitely not be perfect, but it will be good to hear feedback from the users who will try it. Also, Control Z. We deployed it a little bit earlier, but it was quite buggy, and many people were using Control Z just because they expect it to be there, and it was ruining their model, and they probably wouldn't even realize until, well, now that we fixed most of the things. But Control Z still has some problems when you're using groups and components, aka clusters in Grasshopper. So components also have some bugs, but if you encounter them, please do let us know, share what's going on, what's wrong, so that we can fix it promptly. This is it on my side.
and also I'm sharing the Discord server link, so anyone who wants to have any discussion with our community or team, so join us over there, ask any query related to the Beegraphy Design Award or related to Beegraphy if you are facing any challenges. You can share a screenshot and other stuff over there, and we can help you. So yeah, I think Safis, we can start now.
Yes, let's start. Okay, hello everyone. Welcome to the fourth session of the Beegraphy workshop series. We'll be diving into some exciting concepts relevant to excelling at Beegraphy and also the competition categories. Before we go into the workshop, I would like to give a quick intro about our team at Coden. Let me just share this. Yes, so we are a network of architects and designers from across the globe, and we work towards making design innovation more accessible to all. And as a response to all these design education and the challenges that it's been facing, we started Codin Edu. Now, Codin Edu is the education wing of Codin. The aim is to make design education accessible to all, and this is where our vision kind of aligns really well with what Beegraphy is trying to do, and that's how the collaboration kind of started. Now, Codin Edu is part of a larger Codin ecosystem that this includes design projects, design competitions, and design entrepreneurship. We mainly focus on these three as our guiding principles: to explore, to innovate, and to upskill. Currently, we're sharing our knowledge through online workshops, such as the current one. And then we also are present in design studios and other programs around the world. These are some of the courses that we've developed and also are in the process of development, being led by tutors from across the globe. Now, for this Beegraphy workshop, it'll be Ayush, Divya, and me, Saifis, who will be taking the workshops. And yeah, and these are some of the works that have been done at our previous workshops. Yes, so that's a brief intro about Codin Edu, and the three of us will be taking today's workshop. Now, heading into our workshop. Yes, so today we'll explore the final three categories of the Beegraphy Design Awards, which is dynamic structures, building facade, and open innovation. Now, the first session will be dynamic structures. This will be led by Divya. In this workshop, we'll be looking at how you can use Beegraphy to create structures that moves or shifts based on the user interaction or some kind of stimulus. In the second session, which is led by Ayush, will be based on building facades. We'll explore how parametric design can transform facades into more than just coverings. They can become living or breathing parts of architecture that optimizes light and also enhance sustainability factors. And then in the third session, we look into the open innovation category. The key focus here is to design a product that's more transformable and not only creates different variations, but also a positive impact to society of sorts. So these are the main topics that we'll be exploring in the workshop today. And I think that's it from my end, and then we'll head to the workshop. Forward to you, Divya.
Just
Yeah.
a quick update. I'll be
Yeah.
having the first session. The building facades will be the first session, and the dynamic will be the second session.
Okay.
Yes. Perfect. Then let's get right into it. I start by sharing my screen. Hopefully you can see it. So what we are going to do today is the Al Bahar Tower in Abu Dhabi. The building is one of the pioneers when it comes to implementation of parametric design in large scale architecture, and is a wonderful example of how parametricism can be applied onto the facades or the skins of the building. The building is in Abu Dhabi, and it was open for public in 2012, but the design conception was done something around 2007, 2008. So what we are seeing is not, let's say, the most, it holds its relevance today. It is still one of the best example of a parametric building facade. But yeah, there were tools existing and that there were methodologies existing back then, 15 years ago, which were able to facilitate this kind of a generation. And today we are going to see how Beegraphy can help us in doing so. We will not be copying this design exactly, but yeah, this is the base that we will be using. It's a parametric approach in which the skin is like a breathable skin, and the apertures or the openings are controlled based on how much sun we want to let inside. Abu Dhabi, because of its geographical location, is very prone to overheating and so on. So the skin is used as an adaptive uh, facade to control how much sun is allowed inside. It is based on a hexagonal grid. If you can see this, this is one module, and these are the individual elements that can open or close to a state something like this, which is almost fully closed, so no solar transmission, to almost fully open, which allows up to 70 to 80% of the transmission. And that's just small prototype how they were doing, how they conceived it, and the top image wonderfully explains the different states from a very closed, fully opaque facade to a very open and a glazed facade. This was structure. So this whole opaque thing acts purely as a skin. There is no other function. It is not a weather-proof thing. The weatherproofing is done through this glass facade outside. It's a fully glazed building, a hermetically sealed block. And then this skin just acts on controlling how much sun should be falling on this glass block. Some views up close, how it looks like. And yeah, let's see how we can go about it. Let's have a quick look onto the whiteboard, how we can conceive it. So this is a base module, which is a pure hexagon, nothing fancy about it. And in this, parametrically, how we can reduce it is we can take the center point, if you can just see the dot in the middle. And then what we can do is we can pick up alternate points on this one base hexagon, the one which I just highlighted in red. And then based on these 3 points, we can control the opening. So let's say if we can join these 3 alternate endpoints with the center point, we get these 3 lines. And if we get a point somewhere on this line, the one which you can see with yellow here, and later, if we take these 3 points, the 3 black points, and if we can connect them with the yellow points all around, we can get this kind of an aperture. So the area enclosed by this black polyline could be the closed area, and the remaining one will be the open area. So now what will happen, just by moving this yellow dot along this line, we can control the size of the opening. So on the looking from outside, it looks like a very complicated mechanism and how to do it. This is just a simplified way on how we can break it to achieve the same impact with very minimal input required from our side. What I mean by this, again, let's say we are just moving this yellow point along these lines, along all the 3 lines. The yellow dots are moving. For example, if the yellow dot is very close to the endpoint, then what will happen? We will have a complete, when we draw the polyline, it will be almost like a complete enclosure. And right now, just in pink, if we have the dots extremely close to the middle point, then we will have a situation something like the magenta situation, which I just drew. So our parameter of opening and closing now is reduced to 1, where I want to place this particular point on this line. If it is very close to the center point of the hexagon, I am in a fully open situation in facade. If the point moves far back, towards the edge of the hexagon, it is almost in a fully open situation. Now we just have to make it parametrically. Apart from doing this facade, we will also check how the opening and closing of the facade is happening through a concept known as an attractor point. Those who are, let's say, already users of Grasshopper, you might be familiar with this. And then today we will learn how we can implement that in Beegraphy. Perfect. So a pretty simple mechanism. It was a pretty complicated thing, but then we were able to reduce the whole complexity to just one parameter, which is the location on this line, which is controlling the entire opening and closing. And then let's now make it in Beegraphy. I'm sure you are familiar with the interface. If not, just create an account in Beegraphy, completely free, and then go to the editor. Editor will be like your dashboard with all your files, everything stored here. And then let's start with a new model. Give any name you like. Let's start with facade. It all starts with a blank canvas. On one side, we see the geometrical output, and this whole dot grid thing is the grasshopper kind of a canvas where we can do our visual scripting of getting all the components, getting all the elements, and connecting them in a way we like. Perfect. So as we learned, it is based on a hexagonal grid. So first thing we want to do is to get a hexagon. We want to apply it on a facade, but the approach could be that we can create like a small example prototype with a couple or 3 or 4 hexagons. And once the script is ready, we can implement it onto an entire building. If the script is working well, it is just a matter of changing the base surface to whatever we want. To get a hexagon grid, we have a component ready, which is known as a hexagonal grid in Beegraphy. So let's start with that. How we are just doing some experiments right now, so we do not need to overburden our system with a lot of computation, so we can reduce the number of elements or modules here to let's say uh, 3, let's say 2 by 2 modules. So we get a total of 2. We want the radius to be 30, any number, and padding is how much spacing we want. As we saw from the example that literally there are no spacing between the hexagons, so we can just make it as 0. Now our hexagons are, let's say, joined to one another. We can even start with a 2x1 grid to make it even faster. The important thing is to start with not just one hexagon, but at least 2, so that right from the onset, we are not working in singular elements, but we are managing the lists so that whenever, because when we will apply it to a facade, there will be a lot of hexagons, and so that it won't cause any problem later. Perfect. So what we need for once, as we discussed, what we need to do our parametric exploration, we need the center point, which is extremely important, and we need these endpoints to proceed further. To get the center point, we can use the centroid command directly. We can use the points coming out directly from here, but it is better to use a more parametric approach so that even if we change this to a facade or a different kind of a grid where we do not get the center, we get all of them ready. So we got the center here. And to get the endpoints, we can use a component known as explode. The explode component gives us both points and all the individual curves. We are concerned only about the points. We get them. Now we can hide the base thing. Great, we got all the points. Now what we want to do is we want to get the alternate points of this thing, because we will have only these we want only these 3 lines coming from the center on alternate points. To get alternate thing, what we can do is for each of the hexagon, there are 6 points coming. So there is a list of 6 points. So we can remove alternate point and we can create a pattern of false, true, false, true to generate, to cull or to delete every second point. So if we use the component remove pattern from a list, and then if I apply all the points in here, let's see what happens. Let me hide this thing. You see, now we have received 3 points out of the total 6 points. So the one which you see in yellow here, 1, 2, 3, 1, 2, 3. 1 point is overlapping here. So a total of 6 points, 3 each for the 2 hexagons are present. Great. Now, to complete our thing, we need the other 3 points as well. Let's copy this component, the remove pattern. But what happens now is that we are not removing the other 3 points, but the same points. To change the order how the Boolean is function, we can just, so if we just click on the Boolean and we see that it is true and false, that is the default input. So we have to change the default input from true, false to false, true. So for that, we can just take a couple of Boolean. And what was the default thing? True, false. So we have to make it false, switch off, and then true. Enter, and then keep pressing shift, and then enter the second. Now let's see what happens. We see these 3 points, and if I click on this thing, they are the other 3 points. Now we have successfully, let's say, segregated the points. The 3 points are going to remain the same. This one, and this one. And for the other 3 points, we want to create a parameter to move along the line. Okay, to reparameterize that line, first we need to get that line. So it's simple, we need to get a line component. And how we want the line? From the center point to these 3 points. So the first point is going to be the center point, which is this. Let's enter the first point. And the second point is this, the 3 points that we segregated. And it's not something what I intended. What we wanted, that there is a hexagon like this, and from the center point, there should be 3 lines, but we get something funny. It's because we have, this is the line which shows there are multiple lists going on as an input. So it's a tree. But in this input, it is only a single list. So there are these points, the center points of the different hexagons are not corresponding to the relevant points on the edge of the hexagon. So what we can do, we can graph the tree, we can graph the list into multiple branches, and that should help in segregating the points. And this is working well. So what we did, because our other input is coming as multiple branches of a tree, we have to convert it into the same format. Our data should be coming not as a single branch, but as a tree with multiple branches. And that is happening well now. What next needs to be done is there should be a moving point on this line. And to get that moving point, we can use a component known as evaluate curve. Now, this is the input, this is the output we are getting from the evaluate curve. Let me just show you with a small example what happens if I change the slider. If the input is 0.3, the points are here. If the input increases, the points move away. So what is happening that if the input is 0, the point will be closest to here on this line, on towards the center of the hexagon. And as the input value is increasing, the point will keep on going further away towards the edge of the hexagon. So if the input is 1, it ideally will be a fully closed state. If the input is 0.3, it will be like a semi-closed, semi-open state. If the input is 0.1, it is almost a fully open state. Because of the constraints of the geometry of the panels itself, it is impossible that we can get an input of 0, that it is a fully open state. It is so we can create a range of, let's say, 0.05 or 0.1 as the least, as the fully open state. Perfect. Now, what we were saying is that we want to use something known as attractor points to control how the opening and closing is happening. If we are talking about attractor points, let's first construct a point. A simple construct point with 3 range input. Let me change the range to 100. A similar X and a Y input. So now you see this point, this becomes our attractor point. This helps us in controlling how we are managing the opening and the closing of the facade. We can move it anywhere we want. So what we want to do, let's say if this is a grid of our individual modules. There are hundreds of modules, and each square or each block represents one module. Let's say if my point is located here, what I want, the module which is located closest to this attractor point should be opened the most, and the module that is located furthest to this point should be closed the most. So let's say this is kind of an arrow here. So this will be the most open module, and the one which is the furthest away will be the most closed module. And everything in between will be somewhere in between. So it could be partially closed to whatever extent we want. So it is not a stepped progression, but a linear progression. In between the fully open and the fully closed state, all the different possibilities are allowed. And between the extreme modules of fully open and closed, all the other modules will be somewhere in between. What happens if we just move this point? So this attractor point will help us in parametrically control this. If I move the attractor point here, what happens then? This module will become the most open module, and the one which is the farthest, which is this one, will become the closest, the most closed module, and everything in between again will follow the progression. The good part is once we are done with the script, we can easily change the location of this point through these 3 sliders, and the whole pattern across the facade will change. Okay, we have got the point now. And to find out which is the closest and which is the furthest to this attractor point, what we need to do is we need to measure the distance. We need to measure the distance between the center point of the grid and the attractor point we have just created. And to measure the distance, let's do distance, 2 points. The first point is our attractor point, and the second point is the centroid. Now we got the distance for all the different hexagons. Because there are 2 hexagons, we get 2 distance values. If I just increase the value to 3, if there are 3 hexagons, then we will get it for 3 hexagons. Everything is parametrically controlled. Now, the distance we are getting is 98, 90, 133. But we just realized that the parameter that we want to input to control the position of these points in the hexagon, it should be between 0 and 1. So what we can do is we can remap these numbers. Remapping means taking a range and keeping the same sequential distribution, but applying the same values into a different range. In our case, the range will be 0.1, but we decided that physically it is impossible that the panels are 100% open, so we can have the range between 0.05 to 1. Okay, then let's just remap the numbers. For remapping numbers, these are the distance we want to remap. We want to have the source minimum and the maximum, so we can use a simple command which is bounds to get the minimum and the maximum of this list. We got the minimum, let's add minimum to the minimum, max to the max. And this is our target range. The maximum what can happen is a fully closed state, which is 1. And what can happen, like the minimum, is 0.05, as we just discussed. Now let's add this number. Again, what we just saw earlier, that we had to graft the tree whenever the output is like a single list to provide the data in a similar format and all the branch can be read simultaneously. We should graft this output so that the input for our evaluate curve component is in the form of a tree and not a single list. If we do this, what happens? Now, let's first check what the output from the grafting is. So we are getting 3 different output, 3 different trees. The minimum which is happening is 0.05 exactly. The maximum is 1, 0.999, and the other is somewhere in between. Let's see what happens if I increase the number of hexagons from, let's say, 3 to 9. If the 9 hexagon happens, if there are 9 hexagons, and if I just see the list, everything looks okay. The minimum I'm getting is 0.05. The maximum I'm getting is 6, is 1 at this node, and then all the rest are somewhere in between. So fully open state, fully closed state, and all the others are somewhere in between based on their relative distance from the attractor point. What happens if this attractor point moves? Let's keep an eye on these numbers and let's just change the attractor point, all of these changes. So everything is parametrically controlled, the opening and the closing, based on where we are locating the attractor point. Things are working as expected. Okay, so what we have till now, we got these 3 points which were located directly on the boundary of the hexagon checked. Second, we got these 3 lines, and then we got 3 parametrically controlled point on this line. 1, 2, 3 checked. What is the next step? Let me draw it in a blue color. Is that we need to create a polyline connecting all of these 6 points. Once they connect, we get a figure something like this, and then we can just convert this figure into a surface, and we will get at least a surface with an open and closed situation. Okay, to create a polyline, let's get a polyline component. We can provide an input, which is a series of points. To get that series of points, we can merge different points into a list. Total how many points we want to to merge together, total 6 points. 3 on the periphery and 3 on this parametrically controlled line, total 6 points. So let's just add ports, total 6 ports here. And then one thing we need to remember while adding these numbers is that they should be in the correct order. Otherwise, we do not know how the polyline is created. So let's say if this is the first point, this point should be the second point while merging. This should be the third. This is fourth, fifth, and the sixth point is this one. So you can see there is an alternate between a point from the periphery and point from the parametrically controlled evaluate curve output. If we see the 3 points on periphery, they are together coming out as a list. But we do not want to put these 3 points into the same order, but we want to juggle them around. So what we can do is we can use a component known as list item. What it does, it takes a complete list as an input and gives output as a single item at a particular location in this list. So in here, the output is at location 0. The index of the item is 0. There are 3 items, so we should get like 3 output from here, one at index 0, the other at index 1, and the final one at index 2. It will be a bit confusing to see this on so many hexagons because there will be like quite a lot of overlap. So let's get back to only 2 and then identify the correct order of providing this input into our list merge component. This item is this one. So let's make it as the first item and then let's go clockwise. So this is the first item, then this should be the third item. The second item should be somewhere here on the list or on this line. So this is our first item. Let me input into the list merge component as the first. This item you see is actually this one. We are just concentrating on this hexagon now, not on this one. So this should be ideally the fifth input. So let me add it to the fifth input. And this here is the third input. Perfect. Now we need to do the other 3-point input, the second, fourth, and the sixth one. So we have already provided input for our first, third, and the fifth points on the periphery. Now we need to do it on the second, fourth, and the sixth position. And we can follow a similar process of what we did it for the peripheral points, is that we can use the list item because we are facing the same problem. We get an output in the form of a list with multiple points in there, but we do not want to repeat the same order. Therefore, I'm extracting each point separately and then creating the perfect order through the list merge component. Let's get all the points in. First, index 0, then index 1, and then finally the index 2. This was our point 1. So this one should be our point number 2. This is there. So let's add it to point number 2. This is here, which should be our final point, which is point number 6. So let's add it in point number 6. And this goes in point number 4. So now what we have, let's use a panel to check what kind of output is coming from the list merge component. So we have 2 lists of 6 parameters each, 6 objects each, which are 6 points. And it looks pretty okay. We will identify it once we plug in our polyline. We are not able to identify, looks pretty okay, but this polyline, if you see, it is not fully closed. So if we do the Boolean, then it will be closed. Perfect. We are not able to see everything well because there are just two. One, it is fully open condition, which is this, and the other one, which is fully closed condition. If we just increase the number of hexagons, then we will start getting the in-between values as well. And it seems to be working as expected. Let's hide all of this so that we can see everything better. Select everything, and then let's hide. What we see now is just the base grid, which is this, and the centroids for each of them. We can even hide the centroids. We don't need them. And let's now, to visualize it better, create a surface out of it. So we use the component curve to surface. The input is the curve and the output is the surface. And it looks as expected. This is a fully closed situation. This is a fully open situation. And everything else is somewhere in between. This is partially closed. This is partially open, and so on. Let's move our attractor point and then see what happens. You see pattern is changing now. This yellow point here is the attractor point. And then as we are changing the location of this point, the distribution over the grid is changing. Perfect. So we have now achieved a proper distribution on the entire grid. We just have to put onto a facade now. We have to just apply it on a facade. As we saw, our building is more or less a cylinder with just a slight bulge in between. So what we can do is we can create three curves located on top of one another. The central curve is, let's say, slightly bulged, and then we can loft all of them to create the building envelope, and then we can apply this facade, this same script on that facade. Okay, let's create a circle. For circle, I will hide all of this because our, let's say, hard part is already done. We just need to apply it onto the building now. Let's say our base curve is of radius 20 meters or 15 meters, whatever you like. Let's do 15 meters. Origin is 0, 0, 0. Our top curve, will also be 15 meters. And let's say our middle curve is 18 meters in radius, or let's say 20 meters in radius. The entire height, let's say, is 100 meters. So in the third circle, we push it up in Z by 100 meters. This is one of the best part about which I like the most, that for every input, there is no necessity to create a separate number or a range. In the component itself, there is a possibility to provide that input. So functionally, it doesn't add much, but overall in the workflow, it reduces the time consumption and makes the overall script looks much cleaner and makes the process a bit faster as well. And then let's say this is our center curve and we want it in the middle. So let's say at 50-meter height. Let's merge all of them. Add port, another one. So we got 3 input now, and we want to loft it together. We can simply use the loft surface. Let's add all the curves here, and then we get something similar to what the shape of the building is. Perfect. To close it, we can just create curve to surface. And then we can add the top and the bottommost curves there to get a surface there. We added both the surface, so it is like a closed geometry now. So, so let's say this is our glass facade, but we want our skin to be coming outside it. So we can do offset surface. What surface we want to offset is our inner one. So now you can see that there are two surfaces here. The blue one is our inner surface, which is a complete glass thing. And the yellow one or the green one here is our outer surface where we want our grid to be applied, our skin to be applied. We got it as a single surface. Now we can just, let me hide all of the other things. Now we want to get hexagons around because our whole script is based on this hexagons. So for this, in Grasshopper, we would have to install a plugin like Lunchbox to create a panelization. But in Beegraphy, it is a vanilla component. If you go to the tools toolbar and here in panels, you can see that there is already a option for hexagonal panels. There are multiple other kind of panels as well, and I strongly encourage you to try the same script on different base shapes, let's say octagons or squares and so on. As soon as I apply surface on it, we get something. The number of hexagons are very low. Therefore, it is difficult to see it well. So what we have to do is just increase the ISO numbers here. Let me hide all of the other things so that only our shell is visible. Let me do it 20 by 30 and then see whether I'm happy with the grid or not. Let's do 30 cross 15. Okay, perfect. There are quite a lot of hexagons, so there is a possibility that our script might take pretty long to run, but I'm happy with this grid. And the good part is that I did all the exploration on a much smaller, with a much smaller computation power with just a couple, 2 or 3 hexagons. So now implementing it on top of it should be pretty easy. If we want to apply our entire script onto this building facade, we don't have to do much. We have the entire script ready. We just have to change this hexagon grid input. Let's say let me do a relay here. So relay is just a pathway of, so this component contains nothing. It's just a pathway of controls the direction of the flow of information. I don't need two, just a single one. Perfect. Let's add our other hexagon grid input here as well. Let me disable this when I add the input in. And as soon as I will add this component, ideally, the script should be applied on the entire facade. Let me hide this. As soon as I will enable this component, it will take some time to run because we are talking about our grid was 30 cross 15. So we are talking about 450 hexagons. So this is very computationally extensive, so might take a couple of minutes, but as soon as this process is ready, ideally we should get an output of what we initially intended. In the meantime, if you have any questions or any queries, just put it on chat, or you can even open your microphone and ask them directly. Just remember that in Beegraphy, there is no installation, but all the computation is happening on your personal computer. It is not a cloud computing. So depending on how strong your PC, how strong your laptop is, the computation time or the processing time may vary for different people. So yeah, there is a question from Lorenzo.
Hello.
Please go ahead. Yeah.
I have a question.
Yeah.
I mean, concerning the paneling that you just did, I was wondering whether you can, if you model your panel somewhere, I mean, you model it on some other software, like for example, in Revit, you can go on Revit and you create the panel as a family, and then you go to Dynamo and just apply it using the anchor points to anchor that model that you have made as a family. Is it possible to just come here to make the hexagonal shapes and then to apply your third-party family that you have made somewhere else on that? Is it possible?
Abhishek, maybe correct me if I'm wrong, but at the moment, Beegraphy doesn't allow importation from Revit, but I think it is on the cards and will come soon.
Okay.
Yeah. So what I would suggest you is to the best possible situation will be if you are modeling your entire project in Beegraphy, because that is fully possible. Definitely not the BIM information part, but interoperability between Revit and Beegraphy is not possible at the moment. We will have to check with learning when that is coming, but at the moment that is not supported. And it looks like our panelization is complete. Something wrong is wrong here. We are not able to get the remap numbers done well. Let me. Okay. So one problem which is happening that because our whole script was planned with hexagonal hexagonal modules, but you see there are some components on the top, some modules on the top which are not hexagons. So this is what we have to do. We have to, yeah, this one step I missed. Apologies for that. We have to make sure that the input are only hexagons. So what we can do is we can explode the hexagons. Let me reduce them a bit. And okay, let's do it on a smaller surface so that we are computationally faster. Good. It's reloading. Let me stop sharing my screen for a second until it reloads. Yeah, if there are any questions that can be taken, that should be taken right now. Otherwise, the process is exactly the same. As soon as the computation is done, we should see the panel on the entire surface as we saw it on the sample. Yeah, another question from Lorenzo.
Sorry to bother you again.
No, please go ahead.
Talking about a computation taking time to process, and I was wondering whether that process depends on your computer or on your connection speed.
No, on your computation power of your computer.
Of your computer?
Your computer, your personal computer.
So when you're doing that online programming, your computer is still playing some. Okay, I didn't know. I thought everything was done by your connection.
No, I think Larnik can explain more on this.
The process the processing for all those computation which you have just created the algorithm for, happens on your system locally. So all the 3D which you're seeing right now is basically rendered on your own PC. So it all depends on your PC strength. We just host the script online on our platform on Beegraphy. So Beegraphy can, and I mean, cut down those processes of having a file, saving file, opening it in Rhino or Grasshopper, all those kind of other installable software. You can just access it from browser. So this is what Beegraphy provides right now. But the computation happens locally on your device. So a mobile device would be slower, probably. I mean, if it's a low budget mobile phone, then it's a if it's a high budget laptop or a desktop, it would be even faster.
Okay, thank you.
What I would just like to add, everything that was previously said is correct. I just wanted to add that we managed, and so far we're managing to keep the algorithms very light. That's why even on like very basic computers, you're able to do the computations. But if you have two computers, one more on the higher end, it will compute faster.
Perfect. This brings us to the end of session 1. Maybe let's take a 5 minutes break and then we start with session 2. What do you suggest, Learning? If there are any other questions, please go ahead. And you can ask them in the meantime as well. Yeah, perfect.
Did your final output came like the one which you're trying right now?
It is taking a bit more than expected to load. So maybe I can share it a bit later as soon as I get it.
You can probably just try it on a single module. I mean, do it on a single module and delete the rest of it.
Yeah, we already did it on like sample modules, and yeah, it's just about having it on lesser number of modules. So maybe after this session, I can share the final output on what we just created together. Okay, great. And in the meantime, guys, if any question or any curiosity comes to your mind, feel free to put it on chat.
Shall we make the break shorter, maybe? Or you guys
Sure.
want to keep it
I
going?
can start. Should I start?
I wonder if
Yeah, let's
yeah.
start.
Yeah. Okay. I'll just share my screen. Is it visible? Yeah. Okay. So we'll start with the next part of the workshop. It's dynamic structures. And sorry. Yeah. So it's dynamic structures with Beegraphy. And what we mean by dynamic structures is like exploring the dynamism of a design. So it could be stuff like bridges that roll open, or it could be furniture that transforms. The goal is that some kind of transformation is happening, and to serve multiple functions or a single function that modifies as per requirement. And then you can take inspiration from origami, flat packing, fast moving technologies, all of this. And all of this movement needs to be based on some kind of real life dynamic actuators. So these could be motors or simple actuators or pneumatic pumps. It could be any of those pin joints, stuff that can help in mechanical motion of an object. So it could help us create products or structures that can incorporate dynamic, adaptable, and transformative elements. So the example that was available on the Beegraphy website is a bridge designed by Etherbrick Studios. It's a rolling bridge, so it opens and closes based on a pneumatic pumps, which are positioned right at intersection of every unit. And I think we'll be exploring this particular dynamic structure in Beegraphy today. But these could also involve other very interesting dynamic structures, such as those inspired by cab mechanisms. So stingray kind of dynamic structure, which moves as it till the end. And then it could also be watch faces, which are inspired from mechanical motion, or canopy structures that are influenced by, again, pneumatic pumps, which are in the center of the structure. So I'll show some examples of these. Again, it could also be a very simple umbrella mechanism. Basically, how do you simulate a very real life mechanical motion through Beegraphy? So today we'll try to understand it through the structure, but before that, I can also maybe make you understand what dynamism means. So this is one example where you have two threads, and these two threads, as per the rotation and the gravity itself, are basically moving an object. So this distance and this distance and this distance would always be equal because it's the triangle. So this thing basically then moves because of that constraint. Same is with this. So there are a lot of solid objects. Lot of solid unit parts, and those unit parts are just allowed to rotate. They are not allowed to move from fixed connections, but the connections are rotatable, so it makes it dynamic. When a certain object moves, the other objects follow the suit, and then the whole object then becomes dynamic. Same as with the bridge that we are going to explore today. So this is a motion GIF of the bridge. You can see it slowly opens up based on the pneumatic motors that are on the sides. So I'll go back, and again, this is an umbrella mechanism where this particular section moves up and moves down, and because of that, the whole object transforms or expands or contracts. And if we try to understand how such an object would work, is because only this particular motion is pushing it up and down. This member and this member, the sizes of all of these members remain constant. So for simulating such an object, we would first want to understand what remains constant and what is variable. So in most of them, the constants would be the size of the elements. They remain constant.
and the variables would be the pin joints, so the rotation that happens at their joints, that allows for the motion to happen. So if I go back to my slide, if we'll be exploring this particular structure today. It's an octagon structure, as you can see, and it slowly unrolls itself. The base is a dimension. It's basically 8 parts, each of which is around 1500 wide, and then it has like multiple components. The middle trapezoid that you see remains constant, while these are the pneumatic pumps, and they slowly open and close. So the constants that we have is basically the trapezoid. We have the connection from the trapezoid to the top of the pneumatic pump, as well as the location of the pump, which is constant. So only this pneumatic pump goes up and down, and that basically motions the whole structure to move. And if I take you back to this image, you can see that when it contracts, this particular pneumatic pump goes all the way up, and there's a larger obtuse angle here. But when it contracts, it becomes like an acute angle because of the contraction. So these are basically the elements that we would try to mimic. So I'll take you to Beegraphy. So I think you are already familiar with the Beegraphy interface. If you want to start a new model, you would have to go here and create a new model, but I already have a model in place. So I'm going to use that particular script. I'll just have it open. Yeah. So the first thing we will try to do is of the octagon, I would first want to create the base. So I'll first try to create this base. For that, I will just use a simple SDL, which is a line segment. It would require a direction. So point would be our base construct. So if I just write point, I can construct a point at the origin, and that would be our base point. And the vector would be in the X direction for me. So I'll use that. The length of the vector, we understood it was around 1500 in this, so I'll try to keep it the same. Maybe we can go for 160, which is 160 centimeters, and I'll make it a range input. So this would be the side length, and this would go here. So yeah, if I turn it correctly, so that is one of our sides. Now what we want to do is we would want to get the other sides of the hexagon, but it needs to be in a simulated manner. The angle at which this works is if this is a closed octagon, and I make lines through the center, then this particular angle is 45 degrees, while these two angles, it is an isosceles triangle, so these two are equal, and this would come out to be 67.5. So that would be the angle when it is closed. So when we are trying to open this structure this way, these two angles will always remain the same. So all of these angles are the same, basically. So if I want to open this structure, what I can provide is twice of this angle, so that I can get the side on the correct side of it, open to the correct side of it. So all I need to provide is double of this angle, and I'll rotate it along this axis like this. So if I go back to the image, I'll take out the end point. I want this particular point along which it would be rotated, and then I'll just hide. Yeah, so I'll hide that point. We have this point with us. Now I will rotate. So I'll use this rotation. I'll rotate the geometry, which is the SDL, and I will have to provide it an angle, so degree, DEG to radian. the first thing that we have to do when we are providing an angle, convert it from degree to radian. The degree that I told was, now if I take you back here, when the structure is closed, the degree comes out to be 67.5. But when the structure is open, the degree would always be 90, even when the structure remains like this. So we basically are going from 67.5 to 90 all the time. So that is our domain range. So if I take you back here, so I would have to write a range which goes from 67.5 all the way to 90. And this would be our opening angle. I'll use this in the degree. Okay. The next thing we have to give is give it a center. So center, I will use the second point that we have. And then it is asking for a vector. Now vector for us would be the y direction because we are building in the x direction, which is the perpendicular to it. So I'll just put it here. And then you can see it has rotated. But like I told in the whiteboard, this needs to be twice the angle to come to the correct position. So I would have to multiply. I would have to multiply the angle by a constant of 2. I can write here also. And then put this in the degrees. Yeah, so you can see it has already moved. Now if I increase or decrease this, you can see that it is already moving and it is becoming flat. So now I would have to, for an octagon, I would have to do the same step 7 times. So basically in Beegraphy, what we can do is we can make a component out of this. So the way you make a component, and I'll put like a list, merge, just to have a node coming out of this object. I already have a component make, but I'll just tell everyone how a component is made. So you can just select whatever you want to make into a component. I'll also add another node before this, just to be safe with a merger. This goes into geometry and this goes into curve here. Yeah. So basically we are only giving it 2 inputs, the angle and the line segment. So we can just select all of it and then we can create a component. So this component would have a particular name, and if you can go and access it in your Beegraphy workspace. Yeah, so basically you go to my assets and then you go to components, and then that particular component had a G9 in the end. So this would be that particular component. And if you open it, you can see it has in nodes and out nodes, and your geometry is basically inside it. So I already have this in place, so I would directly use it, but that is how basically you make components. So I already have components, and I can go to component here, and then I can use the component, I think it's this one, for what I want to do. So I would have to provide it a curve and the degrees of rotation, and then the output. Degrees of rotation need to be multiplied by 2. I think I deleted that accidentally. 2, and then this would be here, and then this would be the output of it. So you can see it has rotated. Now we have to just do this 7 times. So if I just copy this down, and I'll move these down, and then the output that I'm getting, this particular length segment would then make the other segment. So it's like a continuous looping system that we are making. So you can see that one is there, and then there's another one. Then we have another one. So we have to do this 7 times before we reach the end. Yeah. So now we have a we have an octagon which is closed. But now the interesting part is that this can be simulated. So if I go and change the angle, this one. Now, if I go and change this, you can see it is showing some kind of rotation. I can increase this to point maybe 1, the step. And if I increase this, you can see that it is opening as the angle is increasing. So our first level of simulation is already done, and it is mimicking what we intended. The next levels are basically just detailing this simulation out. So we'll start with the detailing of the simulation. So once we have all of these lines, what we can do is we can bring all of those line segments that we have and construct a geometry in a single go. So I'll just make a list merge component, and I'll add 8 ports to it, just for the cleanliness of the cleanliness in the sequence of the script. So the first was that, the second one would be this, third one would be that. Take it a bit forward. Fourth, fifth, sixth, and seventh. I'll just remove this one. Yeah. Oh, I think we forgot to add the main one. So we can just go and add a port and then move this down. So add a port on the top, which would be this one. Yeah. There seems to be some error. Second, third, fourth, fifth, sixth, seventh, and the last one, eighth. Yeah, so we finally have all of our segments with us. Now the next thing we can do is start making or detailing it out a bit. For that, first thing we can do is make so like we understood, for each of these components, if we have them flat out, we have 2 components. So one is the middle part, and then we have the pneumatic pumps which go on the sides, like that. So the middle part we can just make through the line segment itself, and the pneumatic pumps we'll make from the intersection of these 2. So the first thing we'll do is we'll make these intermediate parts. So now the interesting part is these intermediate parts are based on the geometry, the closed geometry itself. So the angle here would be 67.5. So we'll use that to basically make our inner structure. So of the lines, we'll try and get the endpoints, and then we will rotate. So I'll just open this geometry once, so that it's easier to understand. Yeah. So of the endpoints, I will rotate. So I'll basically rotate this curve this way and that way, so that we get a trapezoid here. So first we'll rotate it at this point. So that would go here. The vector we'll provide is the y direction again. So vector y. Angle we'll provide would be fixed. Like I discussed, it will be 67.5. So I'll write 67.5, and then I would change this from degree to radians. So I'll put this in and then I'll plug that to the angle. And the final thing, oh, I think I chose the wrong component. Rotate would be this one. So this would go here, center, vector, and geometry would be the same geometry that we have. It's gone to the other side, so we can just write a negative in front of the number constant, and you can see we have one side of the trapezoid ready. We can just copy this function and then use the second point, which would be the center here. And then instead of a negative, we can just write an opposite to make it into a positive. Maybe I'll just copy this down and then change it to a positive. Plug that to the angle. So you can see we have the trapezoid ready. I just need to make it into a surface. So I can loft this and this together, but it's lofting it together, so we might have to graft them to have them loft only to the next, only to the curve that is next to it. So I'll have to graft it for both of the lists, and then I can loft the surface between them and get the surface that we want for the trapezoid. Now a shortcut is you can just use edges, surface edges, to extract the curve out of the surface and save some of your time. So we have the edges ready for all of our middle ones. So the middle component. Now we can detail it out a bit further. If I show you in the presentation, it's a shape, and then you have like an offset to the shape, which is the metal interior, and then you have these tiny rails which go and close off the gap. So we'll try to mimic that. So I'll just offset the curves that we have by say 10. We can make it a range input. So width, interior, and I'll put this in the distance. It is going in the other side, so I'll just make it negative. Maybe we would have to provide an opposite to the distance. Yeah, this works now. And then we can just loft between them to make a surface. So I'll move this down. This goes in first, then this goes in. So we have a surface for them. Now we can just extrude this surface. The direction we want to extrude this is the Y. So I will just use unit Y. And extrusion is by 10. I think I'm fine with that. So we have an extrusion, and I can hide off the previous part. So we have a basic body ready. Now we can just make the interior mesh. So for that, I can use the offsetted curve. I will explode it to, I will use the interior curve. I will explode it to get this edge and this edge for all of them. So I will use list item to isolate one particular edge. So if I choose this, it is coming out to be this edge. So I think we would have to go with number 1, and then I think number 3, which would be the opposite of that. Yeah. So then I can just use divide curve or divide by count, and this would give us our first, and this would give us our second. We might have to flip the curve because the direction of the seam would go this way. So I'll just use flip geometry, and then I'll put it in the curve. So now I can use line tool to join these 2 points together, and you can see we have 4 of them. But then I can also increase the count a bit. So I'll make it 8. I'll put a range input count. Yeah, so we have that ready. Now we can just pipe this geometry and give it a very shallow radius, say not 0.05, maybe 0.5. Yeah. And then hide this whole part. Okay, so now we have the internal geometry as well as the internal rails, internal members. Now we can basically develop the pneumatic pump on the side. So for that, I will again go and rotate this particular curve in this direction with the angle being half of what we gave for rotating the sides. So if I go back to where I took out the points, which was, I think, this one. So what I would want is I would rotate this back along this side. So I'll use rotate. I'll use the same geometry that we are giving. And then the angle that we'll be giving now would be a dynamic angle, and it would be from the one that we have in the starting that we were using for rotation. So it would not be a multiple. So I would have to convert it from degree to radians again, and it won't be a multiple of 2. It would be half of it, and I'll use that for the rotation here. And then center would be the point we have here, so that it's rotated on this side, and then we would have to give it a opposite so that it rotates in the correct direction. Now the vector we have to give is the axis of the rotation, which would be the y direction. So vector y. Oh, it doesn't need to be opposite, so I'll directly put this in. Yeah. So as you can see, we have the direction of the pneumatic pump correct. Now, why we took this out is because we want vector which goes in that direction, and the vector we can extract by just getting out the endpoints. So we need to understand which one is the bottom one. So point number 2 is this, point number 1 is this, and we want a vector going from point number 2 to 1. So it would be an opposite vector. So I'll make a vector 2 point, and it would go the other way. It would go the other way. And then I can basically use it to create an SDL again. So I'll use SDL. I am basically trying to simulate this, and how we will do it is, if you have that as your base, so this particular connection to the pneumatic pump will always be, I think I did not make it correctly. This particular connection to the pneumatic pump will always be constant. So this is a constant, but this is variable. The height of the pneumatic pump is variable. So how do we find this point, which basically remains constant? So for that, if this is your object and this is your pneumatic pump, what we can do is we can make a circle centering at this point. So the circle would be something like this, and we can make like a infinite line here. So wherever this circle will intersect with the SDL or the infinite line is where this particular length would be constant. So that can help us simulate a constant length here. So that is the logic that basically I'm trying to develop here. So we have the vector ready. The point would be point number 2, the start of the SDL. The vector would be this, and the length we can give anything. So I'll just give, say, 300. Plug this in. Now we would have to develop a circle here. So for developing that, I can just use the edge of the offset. So the line that we developed, I think it was this no, the other one. So I can just use the endpoint of the line for getting this particular point here, and I would have to just use one of it. So I'll just preview of the other one. Yeah, this is correct. So we have to develop a circle here. For developing a circle, we would first have to develop a plane here. So I'll use XZ plane for that, and you can see it has developed, and then I can write a circle. And the size of the circle, by guessing, it was coming around 65 centimeters. So I'll just put that. So you can see when we're developing the circle, the length from this point to wherever it is intersecting with this line segment is a constant. So even if the whole thing changes, that particular line will always remain constant. So that is a logic, and we will try to find the intersection of the circle and the line. So if I write intersect, intersection, I'll go for 2 points. So I'll use the SDL and the circle. One thing I'll do is I'll just graft it here only so that it becomes easier for us to handle it later. Yeah. Now each of these circles will only intersect with one of the lines which is closest to them. So it's basically unit based now. So we have these 2 intersection points, and we can just isolate one of them. So I'll use list item, and it will isolate this particular point. So I can just preview of this whole thing, and then I will make 2 lines which will basically simulate. So we have this intersection point, and then we will use where we had made this one, and I'll put this here. So you can see we have one line which connects the top of the pneumatic pump to the edge, and this will always remain constant. The second line we want will basically connect the bottom point here to the point there. So that bottom point would be, if we click on this, maybe we can find, yeah, it's the second one here. So would have to graft it, I think. Yeah. So now we have both of those ready, this and that line. I'll just preview of any of the previous ones. Now we can give it a pipe, a thickness. This can be, say, 3. And we can also give the other one also a thickness. It could be, or maybe this could be thinner, and this could be a bit bigger. Yeah. I'll also make like a base for the pump. So for that, I would require to make a cylinder which goes in that direction. I already have the vector for that. So I'll just make a plane from normal, which would be this, and the origin point would be this point. So I'll use this already grafted list for that, and the z direction would be the vector. So vector we have provided so vector we had provided here, and this list also needs to be grafted. So I'll graft the tree for the vector, and then I'll plug it in for the plane. So if I click on this, you can see there are like small planes developed on each of those junction points, which are facing this direction. It's going up. Now I can develop a cylinder which goes in that direction. You can see it is going in the correct direction now because we have basically oriented the plane in that direction. I can give it a radius. So this was, I think, 3. So I'll just go with, say, 5 for the radius. and I will go with a length of 120 centimeters. So this becomes the maybe more 130. Yeah, so this becomes like the body of the pneumatic pump. So only this part will go up and down. This would remain constant. Great. Now we can just mirror this here, or we can basically rotate that there. For that, yeah, for that I can just use where is our last so this is our object, and we would have to just rotate this along this vector 180 degrees, and then we'll get it on the other side. So I'll just use rotate. Rotate, and I'll put this, sorry, this is rotate vector, rotate geometry. I'll put the surface in. The angle we'll have to provide is 180, so degree to radian, and then 180. And then center point that we need to provide would be the one that we have grafted previously, which was this. Yeah, I think this one. So I'll just use this as the center point, and the vector would again be the one that we were using for the cylinder. So this would be our vector of rotation. So you can see it has rotated all of them. And then we can just delete the last one. So I will, it's remove index. For that, I would have to first flatten the list, and then remove the 7th item on the list, and then preview of the rest of it. So you can see we have the basic base of the thing ready. I can basically show you through simulation as well. If I go to my starting of the script and I increase or decrease the angle, you can see the whole object is changing and following the suit. So we are basically first we basically simulated how the base curve of each of these units would move, and then we basically made objects after the motion of that particular curve. So if I show you then we can basically, so this is like one side of the bridge. We can copy it or move the same geometry in the y direction, and then make like a base base to it as well. So I'll just do that. It's basically move. Actually, I've already done this, so I'll just the script is already getting a bit heavy, so I'll just use the script I already have in place. Just disable this and enable this. It's the same script. The last part that I did was basically copied this whole section in the y direction, and then just extruded the base curve in the y direction. So I have something like that. Now I can show you how this simulates. So if I go to the opening angle, I can slowly close it. It's a bit laggy. It would depend on how powerful your system is, but it basically does what we expect it to do. And you can see only the pneumatic pump. So only this thing is changing. The rest of it remains constant. If I show you in a close-up, and if I take it fully closed, it looks something like that. So it's like quite close to what we started from, like this object. And you can basically go and detail out quite a lot more. So if I disable this, so I have another script which was just detailing of two parts of it, just two objects which are close to each other. So now these don't clash with each other, and here you can basically understand the simulation much better. So when I reduce this, you can see only the top points. Only this point is going up and down. The rest of it remains more or less constant. So it's quite a lot more visible what dynamism is at play. Yeah. So that was basically one way of doing this particular exercise. This can also be done through through a looping function, which is still under development. So maybe we can have tutorials for looping function later on. So I can also show you another dynamic structure that is possible. It was this particular umbrella motion that was simulated. In this, you have these as fixed and these as fixed members, and there are places where they are fixed. The only thing that is rotating is this thing is going up, and that is basically affecting the whole structure. So for that, basically what you need is at this point you can make a circle, and at that point you can make a circle, and wherever those two circles will intersect would be the point, would be this point, and then you can just extend this member ahead, and then similarly you can make the whole thing. So this is what it looks. Yeah, this is what it looks like. The same thing, and if I try to increase or decrease the motion, or increase like the height of this point or decrease the height of this point, you can see how it is simulating the opening of the whole umbrella mechanism. And then this umbrella mechanism could be polar arrayed to generate a whole canopy. So I'll just preview of this and preview of a polar array of it, and then you can basically understand how this could be very useful for even these kind of structures. So that's a fully open canopy, and then it can decrease down and basically contract. So I can also make like a tensile fabric on top through Beegraphy, and yeah, the simulation would be possible. So yeah, I think these were the two things that I wanted to show. It would be exciting to see what everyone comes up with. So anyone has any questions?
That was really exciting.
Yeah. It's always exciting to see like the potential that these softwares can get.
Yeah, especially this part.
Yeah.
I mean, look at the kind of detail that the model has.
Yeah.
And how it operates.
It's very like visible when it's like simpler structure. So it might be like really visible if I only make like line work and not the actual 3D model.
Mm-hmm.
So that would be quite visible, like if it's just line work. But yeah. Any questions anyone has?
I think we can wait for a couple of minutes.
Yeah.
And probably we can resume. And meanwhile, if anyone has any queries, please do share with us. Oh.
It's a bit laggy.
Yeah, definitely. It will be quite computationally heavy.
Yeah, it's computationally heavy. I mean, this could be like the individual unit can also be made in the components, but that's a larger exercise. That's why I wanted to do it separately. Then more items would have to be as input and output. Even that could be possible. Okay, should we take like a small break and then 2 minutes break, I think, and then we can start.
Yeah, sure.
I think even 5 minute break could do.
Uh,
People wanna.
Learning is not very audible.
Can you hear me now?
Yeah.
Yeah, I was just saying that maybe we do a 5 minute break, so in case people wanna go powder their nose or take a cup of
Sure.
coffee or
Sure.
I think we can continue.
All right, sounds good. Sheikh, I can't seem to present the options. Okay, I've got it. Right. Yes, hello everyone. My name is Saifiz, and let's begin the third session of today's workshop. The category here is open innovation. The goal is to identify or design a product that can be scaled and could add value to either society, public, or individuals. This can be in different fields: automobiles, wearables, health, packaging, or even architectural scale design relief or some modular constructions. All these fall under the category. Now the key is to identify something that could have multiple variations and can easily be fabricated. Yeah, so with that as a challenge, the example that we've taken for this exercise is a design developed by the Hong Kong Design Institute. It's called Tricane. It is a walking stick which can also be converted into a seat or a chair. Found this to be a quite interesting design. So what we'll try to do is we'll try to uh, create models for both of these and see how these like, it's good that you guys have gone through the various exercise of how structures can be dynamic. So this also has that component to it where some of the features kind of breaks down and then becomes something else or transforms and also adds a different functionality to it. And I think that's the innovative component that we can look at when it comes to this product. And we'll try to model it in a couple of steps. So how this falls under within the open innovation category is that it's lifestyle oriented design. It is easily customizable, also based on preferences and ergonomic needs of individuals. It's practical, scalable solutions and also helping the elderly in their day-to-day needs. And when it comes to the walking stick, what you need to see are these three components. One is the grip handle. You have the adjustable heights and also the non-slip base. We'll try to develop all these parts separately and put them together. It also varies within heights of 75 to approximately 100 centimeters. But coming specifically to this design, it's not just the stick, it's also the chair. So you'll have to see the functionality switch that happens where these legs pop out of the design. And also the handle becomes the seat. So these kind of things we'll try to develop. Now, it'll be slightly challenging, more challenging to design the exact same replica, but we can do it quickly with something that looks slightly similar. But from a functionality point of view, I think this would be good enough. So what we'll do is we'll first try to create a non-slip base, and then we'll create this main stick, a base for the handle. We'll create the handle, and then in that process, we'll also create that dual functionality where when we move a particular slider, we would get this functionality where it converts to a chair. And these are the kind of steps that we'll follow along the script. So the script is broken down into these steps so that you all can easily understand. So in this part, we create a non-slip base, and then we define the length and identify where the stick kind of breaks and becomes the leg. We have to find relation between these two parts, the upper part and the lower part of the stick. We'll also create a structural spine to the stick, create the handle, the legs, the detailing of the legs, because the leg has to break from a cylinder into 3 parts and then fall apart. And then we have to create a seat that becomes a handle, and then connect all 3 together so that along with one slider, the legs gets assembled, the seat also opens up, and then that's it. And that's what we'll try to do. Let me open Beegraphy quickly. Yes. So what we'll do is we'll start with constructing a point. We'll now need to move it to the height of the non-slip base and create a cylinder there. So we'll need points at different heights. So just to break it down again. So we have this part, this is one, and then you have this part, which is the stick. You have this base of the handle, you have the handle, and then the whole thing becomes a chair. Now you can notice this is actually the total length of the stick. So at some point it has to break from here and this has to move downwards. So this joint moves downwards, stays constant, while this goes here. Now you can also notice this height is somewhat similar to the base. So if we call this A, let's say this is also A, and the height is equal to this plus this, which by the Pythagoras theorem, it's root 2A. We'll use this later in calculations when we try to do these movements. So this is what we'll do. We'll try to do this and then slowly build from there. So what I'm going to do is to create points at different heights so that we can then create cylinders and also connect them together with the basic framework. Yes. First step, move it upwards in Z-axis, and let's say we give a height of 0.5 centimeters. And then we'll also do a cylinder on the same point and the same height. Now we also need to select the radius for that non-slip base. We can give somewhere around, let's say 1.2. Okay, so we have that point. Now this is step 1. So we've done this. Now we have to quickly move to the stick component. Again, we follow the same step. We move the point. Let's rename them. So this is our slip. Let's give it a range instead. We'll call it non-slip base. That's good. Step 1, then we'll start moving the points upwards. Again, z-axis. And this one will give height of the cane, which varies between 70 to 100. What we need to do next is that once we get that line, we'll need to identify that point, exact point that keeps moving on this particular line. So for that, we first need to draw a line between the upper point and also this lower point. Cool. So now we have the framework. Now we need to identify this point here. Now for that we'll use this command called evaluate curve. And what it asks for is a parameter number. So something that is within 0 and 1, but falls in this proportion. So for this, we could go back to the sketch and see how we can identify this quickly. As you can see, this is A, and this is root 2A. Now this is also length of this part. So this is also root 2A. Now to get this proportion, this would be, let's say, A upon root 2A plus the whole length of it, which is A. Now from a ratio point of view, it would be 1 by 1 plus root 2, which would give us the percentage of this point, which can be then given as a parameter. But to add equations, you can type math expressions. By creating x plus 1, and then x will be root 2. So we can add square root 2. Yes, so now we have that point. Now that's step 2. Now what we need to do is now break this part and create those two elements. The one is this stick and this stick. There's this and this. So we need to create those two from the points. Now we've already created the point where we need to separate. Now we just need to break them down and access it. There are two different ways to do it. One is you could use this number and shatter it. I think that could be one way to do it. You can select the curve, you can shatter it, the point. Or we can just easily create two lines. I think that would be simpler. One for the upper. This one would be coming from here. Second point from here. The same way you can create the second line, which is starting from here, and then this one comes from here. And that's these two lines. Now we'll first work on the second one, the bottom part. Now what we need to do is to rotate. So we have this line. If you follow the movement, there are basically two types of movement. So one is the vertical movement of this base. So this point in the whole life cycle of its movement, it moves from here till here. So there is one range. Say, well, this is 0, this is 1. And there is another range where this length goes here. Let's call it this is 0 to 1 or 90 degrees. So these are the two movements that we have to simultaneously align. What we'll do here is we'll take the bottom one, we'll rotate it at the base. This line, we'll use the center. This point, and we'll rotate it along x-axis. And then, yes, we need to provide an angle. We need to rotate it from 0 to 90. And also convert degrees to radians. Let's create a range 0 to say this is stick to seat switch. Okay, so now you can see this, the lower half aligned and what happens in its movement. So that's okay. Now we need to work on a similar thing for the upper part so that we can bring this down and make sure it goes together and aligns. So just like how we looked at 0 to 90, the same thing applies for this part of the line, where the point at which this line intersects keeps moving from 0 to 1. Again, another parameter that we might need to remap. Now let's move to the upper line. Thus, we'll have to find that point. So for that, we need evaluate curve. To do it, we can identify a point. By default, it's in the center. Now we have to give a range from 0 to 1, which means when the angle is 0, like when the angle of the lower one is 0, which means it's upright, this point will have to be at 1. And when this point is at the bottom, this will be at 90. And this is what we'll try to match. So for that, we'll use remap. Remap. And then connect it to the parameter. So the source range is coming from 0 to 90, which is the angle to which we'll connect. And then the new parameter will be 0 to 1. And we can just connect this. Let's see what happens. So you see, as it moves, you can see that point move as well. Now what we'll need to do is to get a point at the end of this and then connect it to that point. That's what we'll do. So to get those points, we can get it through endpoints. I can create a line. It's connected here, and then this point is connected here. Okay, so the basic framework of the chair to stick conversion is done. You see how it's moving. Good. So step, actually step 3. Now what we'll do is, so we've done the bottom part, we've done this part. Now we need to set up the upper base for the handle and then the handle in itself. Should be straightforward. We'll do is we'll need to create a let's create this first. So when this is moving down, I think we'll need a base at the bottom. This part. So let's create that. Here. Can hide some of the previous ones. Let's give a thickness with pipe command. Give a radius of maybe 1 centimeters. I'm providing constants now, but this can also be variables which you can adjust later. This pipe is, let's call it inner spine. We'll next create a small base here for the handle to sit. That will need to move this again slightly upwards. Same process, move it in the Z axis. And this will be slightly more than the non-slip base. You can give it a name, handle base height. Create a small cylinder as well. Just the same steps that we did for the base. Base radius. Okay. Make it slightly bigger. Also increase, we can increase the height. This is the handle base. Yeah, it's moving. Okay, so far so good. Now we'll move to the next task, which is to create legs. This is slightly more interesting part of it. What we'll do is we'll try to create, if we look closely, this one needs to wrap around the inner, let's say the inner stick, which becomes the main structural support. You see? So now what we need to do is to that if this is the cylinder cross section, you need to divide it into 3 of them, and then this one has to be inside. So these legs need to fit perfectly when they become straight. So that's what we'll need to do. So you have two concentric circles, and then the outer one is getting cut into 3, and then becomes legs on like all 3 sides. So whenever it folds or straightens, it kind of wraps around the cylinder. So that's what we'll need to do. Yeah, let's focus on the bottom one for now, and then we'll move to the upper part. And here we need to make those channels, right? So for that, an easy way to do it is to get something more perpendicular. So for that, you can use command called perpendicular planes. You can connect this line to it. Yep. So you have these lines. Two of these should do. And what we'll do is we'll create a circle. We'll create a circle on this plane. It'll provide a radius which is similar to, or slightly more, maybe 1.6. And we need to divide this into 3. So for that, we'll do divide, so that we get those points. Divide by count, divided into 3. So now we get those 3 points. Now we can use this command called shatter, which would help split the curve into 3 parts based on these 3 points. Now we just need to access one of it. For that, we use list item. Either way, what we'll need to do is to this is the one that we've got. Now we'll need to rotate it probably, I think, 120, 90 degrees, so that it fits properly at the bottom. So let's do that. Let's first of all, or let's loft it first. Let's create that channel, and then we can rotate it so that it's more clear. So we flatten. Yeah, so we have that channel. I need to rotate this channel and align it properly at the bottom. We can take this point as a center point. So that's coming from okay. I think the axis need to be fixed. The point, so let's create a vector using vector 2 point. Is the same as that of this curve. This one. Cool. We can hide this. Yeah, I think we have it properly at the bottom. What we'll do is so now we have one of it. We need 3 of them. One thing we can do is we can rotate it again. And 120 degrees. We need to convert degrees to radians. And then one more. This will be another 120, which is 240. Goes here. Cool. So we have 3 legs, but only half of it. We need to create the other half. Let's group this. This one will use this line.
There's the vector by 2 points, I guess. They're using.
Okay, yeah, we don't need the vector to point. It's true. Then instead, to create another vector to point. Okay. Cool. So I think we have the base structure for the legs. We need to give a bit of thickness. On side thickness. Give like a 0.1 thickness. Cool. So I think we have the legs. Now if we adjust it. Here. And when it's yes, it fits well. We're done with 1, 2, 3, 4, and we're left with the upper handle. Rest of the things we're done. So this is the main framework, as you can see. And this is the most calculation. The remaining things are more simpler. You can customize your seat, like I've shared in the presentation. What we'll go for is something more simpler. It takes a bit more time to create this custom shape. But ideally, this is better for handle. I will try to attend this quickly so that we get the folding functionality to it as well. So next thing, it's this part here. What we'll do is we'll first create a circle. I think that would be something easier to do. So we'll create a circle. And then create a solid like this, and then subtract to a boolean on that. And that would give us a shape like this. I think this is a bit of a how do you say, cheeky way to do it, but I think let's do this for today. We'll go with the circle, and that circle sits on this point, and that point is coming from here. Give a radius of 10 to 15 centimeters radius for a seat. I think that should be fine. We also have to keep in mind that this will become a handle. So if it's too big, that also wouldn't look good. Functionality wise, it'll be too bulky. What we'll do is we'll create a surface, curve the surface. And a bit of thickness to this platform as well. Somewhere around 0.5 to 2. handle thickness is here, and then we have the handle radius that goes there. Now what we'll do is we'll try to slice this into two so that we get one side of the flap, and then once we do the Boolean subtraction, and once we remove this part from it, the gap for the handle, we'll then mirror it. So first we need to split it. So one way you can do is to create a quick circle or another geometry that goes in that same plane where you want to mirror. So for that, what I'll do is I'll take this point as origin and create an, let's say, an exit plane. Quickly create a circle. It's better to keep radius slightly bigger so that the difference in those commands work well. You give an expression, it's an x plus 1. So it's just one more than the radius. Surface, we have a surface. Okay, so now we have this geometry. We need to split this geometry using our new surface. These are solid, these are cutting geometry. And if we hide previous, we can hide this as well. We'll do a list item to keep one of them. So yeah, and then if we hide this, yes, we have one flap. Now the next step would be to create that void and subtract and create that space for people to hold. And for that, what we'll do is we'll create an additional solid from this point. So let's zoom in a little bit. We need to access the same point. Use a line STL. Currently, what we have is something like this. We have a hemisphere, and we need to create a solid like this, which we can subtract out. So for that, what I'm thinking of doing is create a line in this direction, move it somewhere here, and then convert it into a cylinder or a solid, and then use that solid to subtract it. The way you can do it is now you have a line. Should be a along x-axis. Yes, so that's correct. The length of the line is also okay. It's going outside. What we need is to move it in this direction. Move is the opposite vector, so it's y direction. And 5. Yeah, and then we'll use this line. Convert it into a solid. So you can first pipe it. The radius would be similar to how big of an opening we want. So it could vary between 0.5, let's say 3 centimeters. So this is size. Which we want to move. Okay. Now to subtract both of it needs to be solid. So we can convert it into solid using cap command. To do it, this becomes solid. Once we have that, we can use the solid difference. Solid. When we subtract it with
You tied the other solid.
yep, so we have that void. Now you can adjust the thickness. Okay, so we have half of the seat or the handle. Now what we'll need to do is to mirror it and also connect it with the previous movement. So as this goes to the lowest position, let's say it's 90, and this is lowest, the seat needs to be super flat. And when it's above, it needs to be vertical, so that it becomes a handle. Now, the way to do it is the same. We need to rotate the solid along this axis from 0 to 90, and that will the angle will connect it to our initial slider. Rotate this geometry. The axis is center point. Now the angle is this one, the same slider that we used. We need to connect it back to the seat as well. For that, decrease to radian. Okay, and it has to be reverse. I think we'll need to remap. So one way to do it is use the remap. Then here it's coming from say 0 to 90, right? And then what we'll do is we'll just switch the in the upright position.
Those are radians.
Oh yeah, true. Oh yes. Okay. Thanks, Bernie.
Yeah, no problem.
Cool. So if we hide the base geometry and see if everything's working together, and if that's the case, then we are set. Right, rest and see. Yep, and then if you now play the slider, and just refresh the page. Yep, and that's about it. That's how we can design something like this and create something that's not as good.
The mirrored part was missing. from the seed.
Oh, true. Oh, yes, we didn't mirror it. Let me mirror. Geometry and then okay, now it's done. Cool. If you guys have any questions or if I might have missed out any steps, please let me know. Otherwise, yes, that's how you can develop something like this.
Nice tutorial. I felt like I never needed a cane, but now I do have a chair nearby.
Yeah, it was an interesting design.
Is it patented?
Yeah, I think so. It came out as part of the Hong Kong University. So
It's
I'm
really
not
cool.
sure how much load it'll be able to take, especially if it's an elderly person who gets really tired and wants to sit. I don't think it is. In theory, it works, but I don't know in practice.
Well, thanks for the session, Cephas. If anyone has any questions, it's the best time to ask. I can see that there are some thumbs up. I guess that means everything was clear.
Yeah, I think today's session was. Uh, there was a similar theme going on with those systems, dynamic systems.
Yeah.
It was there. It was there in all the three categories.
Yeah, indeed. Each of those can be submitted for the dynamic design. I think it's also called kinetic design.
Yeah, kinetic. Learning,
Cool.
that brings us to the end of the workshop series.
Yeah, sadly, but I think we're going to think about it. Maybe
Yeah.
if people request, we can do one more, maybe a few short ones, like not three at once, but like one a tutorial per workshop to keep them
Yeah.
shorter. And I think it could be also easier for people to
Yeah.
get engaged for like 1 hour dedicated rather than dedicate full 3 hours. It's quite challenging, especially on weekend.
Yeah. I think each part of it could be developed into a small tutorial, right? The one where like taking one component and doing an array, and we can see those modules replicating like the bridge that Divya was doing, or just the facade module that Ayush was doing. So we take like smaller projects, smaller chunks, and then we zoom in so there's more clarity while explaining.
Mm.
There are three different topics actually. become challenging in terms of, I mean, for somebody to grasp all the three topics content together in a single session. So I think smaller session would have been better. We can do smaller session in the coming weeks, maybe.
And how are the entries coming along?
I
So far-
wish we had more. There are some. We can see number of submissions. Abhishek is following it more with more attention than me. Yeah, sorry for interrupting, Abhishek.
No, I was saying like we are receiving some, and I'm yet to check the recent submissions probably. But I
Okay.
can see a couple of them are there, like new models have come.
Okay, that's good. Well, looking forward to the
More.
entries.
Well, I hope after this session we have more kinetic design in the submissions.
Yeah, it'll be interesting to see what participants come up with.
There is actually one submission that has this. It was furniture. I think it was something like a closet. They with accordion type of doors. Not exactly, but even better than accordion. I don't know how to name it. Maybe like butterfly.
Oh, it's nice.
Which one? I probably missed that. I think. And then,
Yeah, it was actually in the quite one of the early submissions.
mhm.
Well, thank you everyone who joined, and thank you, Safis, Divya, and Ayush. All three were quite interesting. My favorite was this the bridge. I actually liked it. It's quite nice. Was quite heavy. Then maybe it's a challenge for the developers to figure how we can make it work faster. We were discussing it last night, with our founding team. I was hoping we would prioritize web workers that would help smoothen the experience, but there's also one more solution that will help improve the performance. So by the end of this year, we should have better performance. Let's see.
That sounds good. Yes, thanks a lot. Thanks a lot, guys.
Thank you, and everyone, have a good weekend.
Same.
Bye bye.
Bye.
Bye bye.
Bye, everyone.